Watch my back, Nomad.
Good afternoon. Now, this isn't exactly uh, the the game as it looked when it was released. I can't remember when this was. 2005, 2007, or something like that. This is the remastered edition, but uh,
Psycho.
still very
Stay with
cool.
us. Nomad, you're with me.
Check out Crisis. Um, the CryEngine's very famous amongst game engines. Wow, this thing is running at very low frames at the moment. I turned all the details up really high because I thought it'd be fun. But I don't know if you can see how many frames I'm losing there.
Move in on that
It's
train.
not great.
I'm gonna access the
I'm
cables.
going at about 40-45 frames a second, but actually it looks like the stream is worse than that. So it might be that because I'm streaming on my graphics hardware, that even less of the frames are actually going to YouTube.
All right, listen up. Kate here holding a civilian
But
hostage in the village about a cookout.
have a look at some of the
Says
stuff
you wanna
that's
run
going on here, right? Like just the density of the foliage,
gather any intel you can.
for starters, was like a really big deal for this engine.
Priority is to find that hostage.
But the open vistas
Understood.
and
Psycho
the sheer
251
distance
reporting
that
for
you can
good.
render at, there's a lot of what they called volumetric lighting going on in this as well, where you can actually see where the light is casting. So it's like fog shadows and kind of things like that. Um, Simon, there's actually no motion blur on. So, actually, let me check. I'm pretty sure I turned the motion blur off, and I think it's just, oh no! I did turn the motion blur off yesterday. There's settings, you can go low, medium, high, very high, can it run Crisis, which is like totally a meme. I actually had the motion blur off previously, but I don't think it applied it. Maybe that's a bit better. It feels better to me. Ooh, chickens. One less chicken. I shouldn't have shot the chicken. But check out our HDR and our bloom. Looking into the sun's probably not a great idea. Um, One thing I didn't talk about when we were talking about reflections is refractions, which is exactly the same idea as reflections, but talking about light going through objects rather than bouncing off objects. So if I turn on this stealth mode here, you can actually see the light refracting through my stealth suit. And they didn't even have to do this perfectly because it's a stealth suit. So, like, what even is that tech? It's not a piece of glass or something. So, um, yeah, it's this interesting kind of effect that we're getting. I wonder if that's I mean, I don't really have to get into a fight to show you the capabilities of the graphics engine. I think this was one of the first games that could do this. I shot the tree and it broke at the position that I shot the tree and it fell over. That's not entirely, you know, graphics, but then even so it is, because it's the deformation of geometry that we're creating. Um, if I remember correctly, it's not Crisis 1, but one of the later Crises did a lot of work on shadowing, like realistic shadowing. We're actually going to be talking about that today, so this is something that... So, look at me there, and my shadow is distinct and hard and dark. The tree, it is further away from the surface that it's casting a shadow on. The shadow is less distinct, and it's a less dark black, so it's got feathered edges and things like that. There's a lot of the tech that Crysis brought in. Um, I'm trying to think of the things that Crysis invented. I think it was... They didn't necessarily invent all these techniques, but they're one of the first engines to bring in things like tessellation and stuff like that as well. Very, very famous for being very hard to run as well. So they were planning for future graphics hardware. It's a pity that I'm playing the remastered version. I tried to play the original version, but I couldn't get it to run on my computer. So I think, like 15 years on, it had compatibility issues with what's it called? Compatibility issues with current hardware. And I heard from other people that they're having trouble running it as well, so, you know. It's slightly unfortunate, but that's the way it goes. Where am I? Alright. Let me just ditch the EA launcher. It's it's so sad sometimes that, like, I've got Steam, Epic, Xbox, Ubisoft, EA, and I've got a special one for Genshin, but that's just for me, right? I'm just like, why do we have so many launchers for our games? It would be great if we could just bundle them all together. Um, Okay, so a lot of people saying there, Sinio, apparently 3090 can't even run Crisis. Yeah, I'm not actually running a 3090. Mine's a 3060, so it's like I didn't just splash out heaps of money for my computer. I actually did splash out heaps of money for my computer, but I still couldn't get top of the line gear, which, you know, is the way of it at the moment. I think there are a lot of us out there that are just sort of holding our breath until computer component parts start to come back down in price. But to do that, we're going to need cryptocurrencies to crash, so I think it's going to be very difficult, but we'll see how it goes. People are saying, oh yeah, the vegetation is better than the original. Todd Howard would have choice words with me for killing chickens. Okay, so let's get into the lecture for today. So was going to talk about some stuff that is actually to do with Crisis, because we're now, as you can see, the demo games that I've been showing you have sort of been shifting through a timeline into the present day. I mean, some of them I showed you just absolutely present day things, but for specific reasons. But a lot of the ones which are like historically the first games that did such and such, we're at Crisis now, so we're actually starting to look at games that are very close to the same kind of engines that are in current games, and that some of the techniques we're talking about, especially today, are techniques that are just genuinely in use. The second technique I'm talking about today is that. So this lecture is going to be a bit of a brain burner. There's going to be more complex work than there was in the previous lectures, but I think that we've basically gotten through what I would consider to be the foundation topics for this course, and now we're into like interesting things. I mean, like, they're still, I would still consider them foundation to computer graphics in general, but they're not necessarily things that you have to know. I mean, you see the marks distribution for the course. There are marks assigned to the topics that I'm talking about today, but they're like the top end of the scale in a sense. So if you've already got marks for everything else, this is the thing that takes you from like a mark of 90 to a mark of 100 in the course, which is like, I don't know for you, like for you that might be a goal. For me, that was never a goal in any of my subjects. I was just like, you know what, if I can get to 90, I'm happy. Anything above that is like, wow. Actually, I don't think I ever did that. I got 91 once, and I'm pretty sure that was in jazz and popular music studies. I never got a 90 or higher in any computing subjects. So you choose. Speaking of which, I have just released the third assignment, and you will notice the third assignment has a lot of extension material in it. That's because the first two assignments had basically no extension material in it. They're all core competency. So the third assignment has some marks set aside for people that want to do extra, in a sense. So you want to get out there and try out things that I haven't taught specifically, or we haven't put in tutorials, or extend what's in the tutorials to the next step. That's where a lot of the third assignment is. That's why the subtitle of the third assignment is "Show me what you got." That's a real old meme now. But anyway. Okay, so what were we doing last week? Last week we looked at reflections and we looked at post-processing. So we were doing reflections with environment maps and cube map. Wait, that wasn't what we did last week. Last week we did planar reflections, which is reflecting off planar surfaces. I think I was like, you know, when I write a lecture, I have like previous lectures open, and I took the wrong one. This is last week, not last lecture. So we did do this, yes. So we did real-time maps, cube maps. We also did planar reflections, which is like a simpler way of doing it, where we can get away with a single camera for a reflection, rather than like the real-time cube map, which is going to have 6 cameras per reflection, and it really drags on your processing capability depending on the quality that you render the cube map. We also did post-processing. Post-processing, I think, is a sort of a fundamental technique to learn about, which is the frame buffers and render targets, because so much stuff in graphics, in current day graphics, is grown out of the idea that we can render multiple things from different directions, and save some of the information from those intermediate renders, in a sense, and then use them again later for other things. We are doubling down on that today. Both of the techniques that I'm talking about today, which I would consider like, they're the hardest things we're going to do in the course, what we're talking about today, because, I mean, literally we have 2 lectures left. So this lecture I'm going to throw in 2 really cool techniques that, I mean, one of them about shadowing, I really like, in terms of how important it is to how things look. It probably should have come a lot earlier in the course, but it couldn't, because you needed to know a lot more about doing post-processing before you could do it. And then I'm also today going to, actually, let me just, let me go into the things that I'm actually talking about. So casting shadows, but the other thing is I'm going to talk about deferred rendering. So what we're going to talk about today is flipping lighting on its head. So everything that I've taught you about lighting in graphics, we're not going to remove it. We're still going to do it, but we're going to jump through some hoops. We're going to do some convoluted ideas to switch our lighting around so that we can get around a lot of the issues we have with it. I'll talk more about it as we get deeper into it and talk about the topic. So first half shadow mapping, second half deferred rendering. I'm not going to be able to give you like a full-on complete look at both of these things, but I'll give you an overview, and like, you will see how both of these techniques are just extensions of what I've talked about before. So I've talked about rendering to frame buffers, and I've talked about doing post-processing passes and stuff, and with both of those, and you know, a decent idea of just like how to do a render in the first place and how to extract certain information from it, both of these techniques can happen through that. I'm not going to say they're easy though, because I don't think they're easy techniques, but they belong here at the end of the course. So let's get into it. First thing we're going to talk about is shadow mapping. So I was showing you some stuff with shadows in Crisis. Pretty sure Crisis 1 was doing reasonably basic shadow mapping, but with a lot of the corrective techniques that I may not have time to teach you completely in this lecture. But there's plenty of places to look it up. Learn OpenGL, very good resource for this as well. They've got some very detailed algorithms for how to do shadow mapping and sample code that you can look at and stuff like that as well. So pretty useful. So let's look at our Blinfong lighting system. The Blinfong lighting system that we're using is going to be calculating the light hitting our fragments based on the angle of the light and the angle to the viewer. So the angle to the viewer is really only used in specular reflection, which we don't even have to worry about too much with shadows. There's another level of getting reflective objects to literally reflect the light from the scene onto other places, but we're not going to do that just yet. We're just worried about the shadows for the moment. So one part of shadowing is already fine with Blinfong. So if I have my light up here in this corner and it shines down on this little cube here, so I have shaded this cube with my hilarious Microsoft Paint skills here, so that it's brighter on the top left and it's darker on the bottom right. So certain faces are going to get darker because they don't have direct access to that light source. So that part of shadowing it exists, and it works for us in this system, so we don't need to do anything like that. And we can get a lot of stuff to appear reasonably realistic because of that. The thing that we're looking at, though, is this kind of shape. That's not even the right shape anyway. Don't ask me to do artistic physics or anything, but the light that should be hitting this cube and not reaching this plane, in our normal Blinfong lighting thing, that light just reaches that plane, because the only thing that we do to calculate light is the angle of the light to the surface. So the angle of the light never thinks about what it might hit along the way. But we know the physics of light runs in a certain way that if the photon hits this, it's going to bounce off in another direction. It will not continue through that object, especially if it's an opaque object, which is what we're dealing with in this situation. And generally, if we're thinking about casting shadows, we're thinking about things that block the light. So the Bloomfong lighting system that we have has no detection of occluding objects. It is not capable of saying there's something in the way, the light shouldn't reach it. So this will still be lit as if this cube isn't here. And so that's something that we kind of want to we want to deal with. We want to make sure this works because it's a little bit awkward otherwise. So, good old question. I think I should have asked this question earlier and put it as a meme through the whole course. It's like, what would ray tracing do? So let's think about what ray tracing would do. If ray tracing is just going to send out billions and billions of these little light beams, like I didn't draw too many of them, right? Because I just wanted to like show this as an example. But there's lots of these different rays of light, and they're hitting this scene. If the rays of light hit an intervening object, then they will either be scattered by a diffuse object or directly reflected by a specular object. I should say fragment rather than object, because the objects can have parts of them that are specular, parts of them that are diffuse, that kind of thing. Whatever happens though is that direct ray of light that could hit this little area here won't reach it. So what we're going to see is these areas of this plane are fully illuminated by that light, but this area of the plane is not illuminated by that light because the rays from that light would hit this box and not hit that. So this is the model we're looking at, right? And this should be reasonably self-evident to us because most of us live in the real world, where if you go outside on a sunny day, you see shadows, right? And we expect to see shadows, and we have an intuitive understanding that objects will tend to block light, which means that there will be areas that receive only ambient light. They don't receive direct lighting from a light source or anything like that. The downside to this, which is something that we have discussed many times, is ray tracing did not magically get easier in terms of time complexity or cheaper in terms of your hardware to run in between the last time I talked about it and now. So all the arguments that I've given about ray tracing are still the same. It's still expensive. So what can we do that's more efficient? What can we do using a current rendering technology? So anything that doesn't have the letters RTX on it on your graphic. I'm looking at mine right now. What do you do if you don't have that technology but you still want shadows? Especially considering shadows have been in games since like the first shadow mapping is probably coming in around, I'm going to ballpark this, around 2005, I think, around there. It was before Crisis, but not that much earlier before Crisis. So shadow mapping techniques, I always think around 2005, because it's around the time that Half-Life 2 started really pushing what we should do with graphics engines. So I think it was like, this is like the end of the era for the Quake 3 engine and the beginning of the new era when Half-Life 2 started building their own, the Source engine, and CryEngine started coming up. So this is before the kind of the ascendancy of the Unreal Engine, which is now, I would potentially call the current Unreal Engine the standard under which other graphics engines are measured against. But you know, so we're talking around that era now. We start to get the idea we want these shadows to appear, and we don't want them to just be a blob underneath someone, because you used to do that. You used to drop shadows, and that's in the 80s. Arcade games like Street Fighter 2, good example. They had just a blob underneath the character, and it wouldn't take where their arms and legs were going or anything like that, but the shadow would give you a placement for the object in the scene, and so it was still helpful even if it wasn't correct. But anyway, how can we do something more efficient than ray tracing using the technology we have? So we're going to be trying to decide what information that we need. So the information that we're missing in Bloomfong, so looking at the tech that we have, we're missing the detection of intervening objects. That's the most important thing. It's like, if there's a light and there's a fragment, is there anything in between the two? And so if we were to just draw a bunch of lines in between the two and do collision detection, we're basically at that kind of ray tracing thing where it's going to become inefficient to do this. This isn't the first time we've had that kind of issue. So what we can do now is we can say, like, do we have anything in our current kind of tech capability that gives us this information? Can the light reach the objects? And we do, because there's one thing that we have been using for think all of our rendering from week 2 to 3 onwards in this course, there's one thing that we've been using for everything, and that is the depth buffer. So every time that we would render a scene, we would actually be sorting objects. Well, not actually sorting, no, it's not sorting, should not use that keyword, but we would be detecting how far away objects are from us, and we would be storing that information in a depth buffer, which is like a frame buffer. So all the pixels on the screen, for each pixel I've rendered multiple fragments. Each of those fragments has a depth value that it's like a normalized depth value. You remember this, right? 0 to 1. I talked about this in detail. And whichever thing has the lowest, is it lowest or highest? White is further away. Yeah, lowest depth value is the thing that actually gets put on the screen and ends up in the frame buffer. So the depth buffer will tell us the closest visible object to something, and will tell us how far away. It's rough, right? Because it's in depth coordinates. It's not in world coordinates or anything like that. So if I have the capability to do a depth buffer, and I can do it from my main camera, it means I can create a depth buffer from any camera. And now that we've seen from things we've done with reflections and other things, we can place an arbitrary camera anywhere in our scene and render from its perspective. So here's the trick. We take our light source and we render the scene as if our light source is a camera. So here, what we have, you love my beautiful artwork, right? We have a camera and we put the camera where the light source is. So all I've done is I've taken that image that I drew before, erased the light source, and put this camera here instead. And what we do is we do a render from the direction of the camera. And this isn't a full render. It's just a depth render, so we don't have to do a lighting pass. In fact, if we've replaced one of the lights with the camera, we can't really do the lighting pass with it, right? So we're not doing our lighting calculations here, but what we're doing is we're rendering the scene from the viewpoint of our camera and getting a depth map. So the depth map here is like a frame buffer, where further away things are white, closer to us things are darker. So I've exaggerated this by coloring it in. So like the closest corner of this cube is black, so it's really, really close. And the furthest edge of that plane is white, and the background in the frame buffer is pure white because there's just nothing there. So that's the maximum depth. So this is what it looks like from the camera's perspective, from the light's perspective, purely on distance, right? So the values in this depth buffer are a full 1 here and a full 0 here. I mean, it probably wouldn't be a full 0 because there is space between the camera and the object, but it would be darker here and lighter there. So this way, what we have now is a record of which surfaces, which fragments, which pieces of our scene are visible to the light. If they're visible from the light's perspective, that means they receive light. Anything that is not here, so behind this cube, there are a bunch of fragments here that the light can't see. So if the light was looking, it wouldn't be able to see these fragments. So now we actually have a record, in a sense, that allows us to say the light can light these parts of the scene, but the light will not light the parts of the scene that is not that aren't visible to it. So rendering like this, we get the following information. We get a depth buffer, as I showed you there, and the depth buffer is going to show us which are the closest visible fragments to the light source. So it's like from the viewer. So yeah, from the light source, yeah, I'm just looking at what I wrote here. Yeah, what we're getting is the depth buffer rendered from the light's perspective tells us where the light reaches. And in a sense, it also tells us where the light doesn't reach. So what we're going to do is record this thing, this depth map. So this is our depth map from our light's perspective. Some people call it a shadow map as well. It's kind of, I prefer to call it a depth map than a shadow map because it is literally the opposite of shadow map. It's the bit that is not in shadow. So I prefer calling it a depth map than a shadow map, but some people call it that because the whole technique is called shadow mapping because it's 4 shadows. So I have a depth map from my camera's perspective. And I have another camera, which is my main camera, that says I'm looking at the scene from this perspective. This is not giving us shadows yet. This is giving us the idea that there is some way that we can detect what the light can see, but that it doesn't actually have any context for us from the main camera's view. Because the main camera's view is going to look at this thing and go, I don't know what you mean. Like, how does this make any sense to me? If I'm looking at it from this perspective and you're up there and yeah, you've rendered from your viewpoint, how do I tell that this is the bit that you can't see, or that these are the bits that you're going to add light to, right? So what we need to do now is to be able to flip this thing back and forth between the camera's perspective and the light's perspective. So this is what we do. We're going to transform between these perspectives using the ideas of the model view projection transforms that we did very early in the course. So we're not going to go for a projection necessarily, although you can, but we're just going to, for the moment, use a view transform to go back and forth between one camera's view and the light camera's view. So I'm rendering a fragment in the main camera. So I'm looking at a particular fragment and I know what the fragment's position is. So if I know what the fragment's position is, I've got its world coordinates. I can put its world coordinates into a view transform. But instead of it being the camera's view transform, you remember the camera's view transform just flips everything into the camera's perspective. This time I will use the light's view transform to transform that fragment into the light's perspective. And if I transform that fragment into the light's perspective, it will be in this perspective. So it would be transformed into the perspective of how the light would see the scene. So we've got a point somewhere, and we transform that point from the main camera's perspective into the light's perspective. I should make sure you can see it, into the light's perspective. And then what we do is we measure that so we can compare the depth value of the light's depth map with the depth value for the current fragment depth. So the fragment that we're looking at, and we say, is this fragment the closest fragment to the light? And if it's the closest fragment to the light at that particular position, then we're going to be able to see we're going to be able to see whether the light is actually hitting that fragment or not. So here's a side-on view of that. This is from Learn OpenGL. So we've got our light here. It's a similar position to the one that I had. They're using a directional light, which is totally fine. You can do that. And they're saying, when I render my depth map, I'll have my cube like I did there, and I will see that I'm hitting that cube, and I'll see I'm hitting the other parts of the scene there. If we're viewing from over here, we have our fragment here called P, and then what we will do is we'll say, transforming this into the light's view space, we can then check the depth map of the light's view space of where it would render that fragment. So which pixel is it rendering that fragment at? We will know which pixel is rendering that fragment at, and we'll say, what's the depth that you have written in your depth buffer there? And we'll say, oh, I've got this depth here of 0.4. So the depth of 0.4 means I can see something in the scene. And then we say, no, wait, the fragment that we're asking you about is depth 0.9. So if we're asking about depth 0.9, and the light says, no, I see depth 0.4 there, that's our information there. So that means that the fragment we tried to render was somewhere behind this cube. And it was looking at these kinds of depth values, so this like light gray depth values, but instead we got this dark gray or this black depth value, which says, no, that's not the object. The depth you're looking at is different from the closest object that I can see from the light's perspective, and so at that point it will not receive light. So that light will not affect that object. So if we get into this situation, but like if we were looking at, say, this fragment here, and we'll see there's nothing intervening between the light and the object, the depth value from the light and the depth value of the fragment will be the same, and we'll say, okay, we receive light from this light. So that's how we're going to get around this. Instead of having to cast lots of different rays, what we're going to do is we do a single render pass from the light's perspective. And then what that's going to do is tell us everything that the light can reach. And then we're going to test by switching between the two different coordinate systems, in a sense. Like the world space coordinate system will give us our fragment position, and then we try to get that fragment position from the light's perspective to see how far away it is. And we see how far away it is. If it is further away than what the light thinks it can see, that means there's something in the way, casting a shadow. If it's the same distance, that means it receives the light. So I think here I have the the overview of the entire process. So what we would do first is we render to depth maps for every light in the scene. It doesn't have to be every light. Often we can get good enough realism in what we're doing by casting shadows just from, say, our main directional light source or something like that. Oh, it's very interesting though when you're doing it with a directional light. You know, directional lights don't have a position, they've only got a direction. You have to choose one. So you have to go, okay, we have to render from this position. We can, however, with a directional light, we can do an orthographic render. Instead of a perspective render. That will do it. So I don't know if you remember, we didn't really cover them in great detail, but an orthographic render is one that doesn't have a widening viewpoint and a vanishing point to look at. Instead, it looks straight on. So it's the kind of render we would usually use for two-dimensional games and stuff like that. But it works pretty well for directional lights as well. Even an orthographic render needs a position to start this camera from, because it needs a near plane and a far plane. But if you keep your near plane outside your scene and your far plane outside your scene on the other side, you should be okay. So anyway, we render from whichever lights in the scene that we want to be part of the shadowing process. If you have small point lights with a lot of attenuation, maybe you'll get away with not casting shadows. However, if they're really close to people, then maybe you do want them to cast shadows so that people can see clearly. Like if someone's carrying a candle around, you kind of want shadows to happen for that as well. So you see how it goes. So we get a depth map for each light that's going to cast shadows, and then we have a view transform for every light. So we're going to be using the view transform kind of backwards in a sense. So we're actually going to invert our view transformation so that it goes so we can go back to the view in a sense, rather than transforming things to the view. I don't know if I'm explaining that the right way, but the maths has to go the other way. Anyway, when we're rendering one particular fragment from the main camera, we find the fragment's position. And then for each light in the scene, we can transform. So this is like part of your lighting pass in a sense. What you do is you transform the fragment position into the light's coordinate system. So into the light's perspective. And then we check the depth calculated for the fragment position against the light's recorded depth map for the things that were closest to the light. So if it fails this test, if these numbers are not the same, or basically if the light's depth map is a lower number than the fragment's depth, then we know that there's something intervening. There's something in between the two, and we would remove that light from the lighting equation. There's different ways to do this, actually, because some people will remove the light from the lighting equation. Other people will add an arbitrary shadowing amount to this to reduce the light received by the object. And this is where you get a lot of like that stuff I was showing in Crisis at the very beginning, a lot of fancy stuff where you can say, let's also measure the distance between those two depths. And if the distance between those two depths is very high, then the shadow has less effect. If the distance between those two depths is very close, then the shadow has a stronger effect. Those are details we don't really have to go into, but those are add-ons that people have done over the years to this. So we can then calculate the lighting for the fragment with that light removed. So other lights in the scene could still potentially reach that, but they will also have to test their own depth maps against that fragment to see which lights can reach that fragment, or which how much light's actually going to reach the particular fragment based on which things are shadowing or not. Okay. So a quick analysis of what we're doing here. We've got a basic technique, which is to say that what we're doing is we're going to render the scene from the light's perspective. And then we're going to do comparisons with that and see whether each of our lights is going to affect a particular fragment or not. So what are the good things about this? The nice thing about this is we've gotten out of needing to do something like ray tracing for shadows. I mean, nowadays people do ray tracing for shadows, so it definitely works. But we get a reasonably accurate model of whether light can reach a surface or not. And we do it without needing the cost of bouncing a bunch of rays around our scene and doing collision detection and things like that. So what we've done is leveraged the way our technology already works, the way our rendering systems already work, to just use another rendering system that's exactly the same as our view rendering, to see whether things are in shadow or not. So this is the classic graphics pipeline technology, where you say we have a constricted pipeline. We don't have like a CPU level capability to do many different types of calculations. What we really do is we do pixel calculations. So we do fast multiple, well, it's not really that fast, but anyway, multiple parallel floating point operations. So we go, let's just use our multiple parallel floating point operations to do this, or render it like it's a normal scene. So what we are adding, however, to that is potentially bad, is we are rendering the entire scene an extra time per light. It's not as bad as it looks, though, because we're not doing the lighting calculations for each light. We're just doing it like a geometry pass, I would call it. So we're looking at things and we're saying, how far away are you? That's the only thing we need to know. We're not going to calculate the lights. We're not going to calculate reflection angles or anything like that. So this is a cheap render. It's not nearly as expensive a render as a reflection render, which does need to do lighting in its render pass. So this isn't too bad, but you are still rendering the scene an extra time per light. You are also using up memory, so every light now has a frame buffer, so you want to figure out how much memory you have on that graphics card. But as I said before, currently, we're not too worried about that, because it's like one of the only numbers under which you can record whether a graphics card is better than another is the amount of memory it has on it. And that's not actually even remotely a measure of whether a graphics card's better than another. But because marketing sometimes requires a larger number in order to put a higher price tag on something, memory is one of those things that has grown in graphics cards. And in the early days, it was necessary. In the early days, just to start these techniques, you'd be like, how much VRAM do we have? We're gonna need a few more megabytes of VRAM. Imagine only having megabytes of VRAM. Yeah, right. So nowadays, when we're putting like 8 gigs of VRAM in our graphics cards, we're not really running into these problems anymore, because the size of memory, we're talking about megabytes to gigabytes, we've multiplied the size of memory by thousands. But we have not multiplied the number of pixels on our screen by thousands. Like the number of pixels on our screen is like, it's going up, but it's a pretty flat line that it's going up at, and it's a pretty low gradient. Whereas the amount of RAM in our graphics cards has been multiplied by thousands. So it's this big kind of more of a Moore's law curve. So we're not too worried about memory, which is why I didn't even put it here in the cons. But there are other things to think about. Is our depth map accurate enough? Is this depth map organized in a way that's actually going to give us correct shadowing? And I'll show you this in a second, because there could be sampling artifacts from the depth map. And also, is your depth map wide enough? Like, if you have a point light in the middle of your scene and it's casting shadows in every direction from where it is, how do you render a 360-degree view around an object? Our frustums do not expand that wide. If you try to create a 180-degree frustum, like a 180-degree field of view, it breaks the graphics tech, because the near plane and the far plane end up on top of each other, and you end up seeing nothing. So there's a lot of issues there with which direction you can cast shadows in if you're going to do them as if you're doing screen renders, which is actually a really limited viewpoint. sort of okay for directional lights, harder to do for point lights. So there's a couple of these things, and I'm going to look through this now because there are some issues that are well known that we can look at. So this first one, hilariously, is called Shadow Acne. I don't know where this name came from, but it's a pretty funny name, and it's a particular artifact that comes from the fact that we are doing depth mapping. So when we do our depth map, it comes from the light's perspective. And we're not expecting the light and the camera to be in the same place. I mean, there will be specific times that the light and the camera are in the same place. But honestly, if the light and the camera are in the same place, you don't care about shadows. Because if the light and camera are together, like you've got a head torch, you literally can't see the shadows because the light is at the same place as the camera. So the light's always, when we're looking at shadows, going to be somewhere else from the main camera, which means it's going to be hitting surfaces at a different angle that the main camera is hitting surfaces. This is kind of okay in some circumstances, but think about it, is that no matter what happens with a depth map, it's going to be made up of pixels, and each pixel is going to have a depth. Each pixel is a square shape. If we sample into our depth maps texels, we're going to hit a particular texel. So it depends on our sampling. We're going to hit texels, even if we're blending between multiple texels, so we're doing a multi-sampling kind of thing, we're still going to get these potential issues where each depth point that we created that depth map with, so everything we did in our render to create those depths is going to be just from the viewpoint of the from the light. So if we're sampling the depth map, we may not get exactly the correct depth because the fragments that we see from the main camera may not be the same exact perfect position as the position, the fragment position that the light's camera saw. So if the light's camera is on an angle to the surface, let me show you how this surface can accidentally cast shadows on itself. So my light has sampled the surface from its angle, and it said, okay, this is exactly the depth that I have here. So I'll write this to my light map, my depth map texel. The depth map texel then, because it's a square texel, exists as this depth for the entire surface of that texel. So this is hyper exaggerated here. It's really big so that you can see it. But the ironic thing about this is it doesn't matter how big it is. It's always going to cause this problem, no matter how big or how small your resolution is on your depth map. So on an angle, this looks fine to us because it's like, yeah, it's this depth, and then so this plane that we've got here is like tilted away from me, and I go, yeah, it's this depth, and it's this depth, and it's this depth. But because each of those texels is effectively flat, we have this depth, then this depth, then this depth is what we're seeing here. Which means that if we're sampling the actual surface here from our main camera, say our main camera is looking straight down on this. So I take this fragment here, and I say, am I in front or behind the depth map? And we look at the depth map, and the depth map says, for that fragment, I'm in this texel here. And it'll give us the distance to this point, not the distance to the point we're at there. And so what it'll say is, this is my depth, this is your depth. There is a discernible difference between the depth in the depth map and the depth of the fragment that you set, because there's this little gap here in between the two. And it'll say, oh, that thing's in shadow. And you look at the scene and you just go, how is that thing in shadow? There's nothing in between them. But because of the sampling inaccuracies here, the surface depth that the depth map sees is a jagged surface depth as opposed to the real surface depth. And so if we're looking at this thing flat on, and the funny thing about this is it doesn't even matter if your viewer is flat on. If your viewer's on an angle and your light's flat on, you can cause the same problem because you're sampling you're having the other problem. And I could increase the resolution of this depth map massively So I could make it so much so that this little jagged line is really, really close to the surface. It doesn't matter, because 50% of that surface would have the jagged line in front and 50% of the surface would have the jagged line behind. So increasing the resolution of the depth map doesn't actually help us here. We have the same issue. So the surface here throws shade on itself, which is a real rough thing to do. So the surface throwing shade on itself means that these areas here, so this will be lit as if it's lit because it's like the depth map is behind it. But here, it's going to detect an object in front of it, even though it's itself. So, this is a simple thing, but it causes really, really big issues like this. I'm glad people appreciate the throwing shade joke. Okay. So don't throw shade on yourself. The way to get around this is to add this thing called shadow bias. So during the shadows calculation, what we can do is we can effectively move the depth map into an object or into a surface. So what we can do is we can say, like, shadow acne is the idea that an object can cast light onto it, can cast shadow onto itself by accident. So what we want to make sure is that in this case, the depth map for the object is never, I'm not sure what that is, but anyway, the depth recorded in the depth map will never be in front of any possible fragment that's in the object. So what we're going to do is we're actually going to take the depth map and move it into the object. So if we want to do this in a really, really simple fashion, what we do is we take the entire depth map after we've rendered it and we just add to it. So if we add a small amount to it, it just pushes all the depth values back a tiny bit. And so if all those depth values just move back a little, they'll move into the objects that they were detected. And so now it doesn't matter which fragment I sample from here, none of the fragments will ever be behind any of the possible values in this jagged depth map, because the depth map has moved inside the object. So now the objects will never cast shadows on themselves. So that sounds good, right? It sounds like a good solution to this, and will get us decent looking shadows. The downside to this is Peter Panning. I just love the names that they came up with. Like, whoever was doing all the research in Shadow had a nice sense of imagination. So Peter Panning is where the shadow actually detaches from the object itself. So if I have a plane and an object sitting directly on it, and we expect the shadow to come just directly off the side of that object, if our shadow bias is too strong and has shifted from the light's perspective, say the light's over here, and it's shifted the things into the object, that's actually going to shift where the shadow can appear. And so what we're going to get is parts that should be in shadow won't be in shadow. And so there'll be this weird ring of light around the object and the shadow appearing only after that. So that's this Peter Panning where the shadow actually gets offset by the fact that we've used a shadow bias. Actually, I don't have any more slides on that, but I can talk a little bit more about it. So there's a lot of different ways around this. So instead of the kind of naive solution where we take all the shadows and we take the depth map and we just move them further away from the light, what we can do is we can move them into the object instead of further away from the light. So what we can do is we can take the surface normal of the object and move the depth map into the surface of the object rather than just directly away from the light. So what we're going to need to do when we do that is actually decide when we're sampling between the depth map and the object fragment, is we look at the surface normal on the object fragment and then we move it then. So there's different ways around this that are differently detailed for different purposes, in a sense. Okay, so there was another issue with the depth map, which is like oversampling, which is the idea that if we have something from the light, so I've drawn my frustum here from the light, and so it's got its boundaries of 0 to 1 in each of the coordinates, and its depth map is going to be this shape. So if this is a point light, I mean, I've really exaggerated this to show you this issue. If this is a point light, it can detect shadows only in the render that it has done. So only in the direction that it has rendered. But what if its light comes down here? Because as a point light, you can shine in many different directions, and it hits this object, and we're trying to render this object here. What happens when we sample our depth map? So if we're sampling it outside the frustum, we're not going to get any depth data from it, or it really depends on our sampling settings. If I'm doing my repeated sampling settings, then it's going to take this area and it's going to cast shadows based on what it saw here, over here, and over here, and over here, and over here, and stuff like that. So we definitely don't want to do some kind of repeated settings. Maybe we want to do some kind of clamped settings. So whatever it was at the edge of this is the depth that it has all the way off into the distance. That kind of works. Actually, that's not clamping. That's I can't remember what it was. The different texture sampling settings. But it's the one that takes the border, and then I think, is it border sampling? Yeah. And then it takes whatever it was on the pixel on the edge and then extends that off into infinity. So if we do that, we're never really going to get an accurate shadow on this object here. So we need to then adjust the way that we're sampling from this depth map to make sure that we're going to get some kind of reading outside of this frustum here. So if we're trying to correct this, if we can't detect the obscuring objects, then we shouldn't cast a shadow at all. That's a rule that we could use. So we can say, oh, clamp to edge was the one I was looking for, so not clamp to border. Yeah, so if I'm viewing my scene from my light's perspective, and I can't see all of the scene because of the frustum, just lining up my... Yeah, if I can't see everything because of the frustum, then we just have to let everything go on the outside. So if we were clamping to 0 or something like that on the outside, or clamping to the edge, we may have some issues, because what we would do is we'd say whatever was on the border of our depth map, that's going to be the depth that we're going to compare everything against. And so you'll get situations where things won't be shadowed properly. Oh, I didn't put any pictures in. Oh well. If you want to, Learn OpenGL has some pictures of this. So what we could do if we want to is make sure that we don't cast shadows anywhere where we didn't make our depth map. So we could just say, we'll put a border around our depth map, which is the furthest depth, 1.0, and we say everything outside that is 1.0. And so that's fine most of the time, but it depends on how far away that light is from the scene and what our far plane of the light's render is. So if the far plane of the light's render, if this is the far plane of the light's render, this is exaggerated, right? Because you wouldn't want the far plane to be cutting halfway through the scene, but there's a chance it could. So if your far plane is partway through the scene, and then there's objects behind the far plane, they're going to get shadows, because the maximum depth that you could show was the far plane. And then this fragment here would be rendering as if it had a depth higher than 1. So what we'd then have to do is just put a little check in to make sure that if the fragment distance was higher than 1, and the depth map itself was 1 or potentially higher, depends how you're actually sampling your depth map, we would just apply the light to that fragment. So we have this kind of situation where, let me just because there's actually some images of that in here, which is interesting to look at. There's the Peter Panning effect. So here we have this one where the light, its frustum ends here, and so for some reason this whole area here is in shadow, even though it hasn't actually had anything intervening there. And so one thing we can do is we can say, all right, we do the oh, it is clamp to border. Yeah. So we do clamp to border there, and we make that 1.0, and that's fine, except for where the far plane intersects with the scene at some point. So then we take the clamp to border and we go, if the z coordinate of the of the fragment we're trying to render is higher than 1, then we're not going to apply shadow to that. So they actually have a shadow number that they're using here. And so there's no shadow, and then we get full light there. Those aren't the only issues with shadowing. There's also the fuzziness of the edges of the shadows and things, and that's more stuff in there that you can look at if you're interested. But limited amount of time today, so I just wanted to look at those things. So, oh yeah, here we go. I knew I was thinking that, so I did have a slide for it. So the shadow mapping, because again, it's the same kind of situation as the issues that cause the shadow bias and stuff like that, is that we tend to get these jagged edges on our shadows based on the resolution and the angle of the light's depth map render. So we get aliasing based on the perspective and aliasing based on the projection that the light's actually looking at. So we can smooth those out. And what's it called? PCF? PCF. Yeah, which stands for, if I remember it correctly, percentage closer filtering. So it's ways to check where the shadow is and give it a fuzzy edge, which is the same kind of fuzzy edge that we'd expect from shadows in real light. I'll let you look that up yourself if you have time. There's also more techniques for shadow bias, but I actually looked at them a little bit today. I was talking about using the surface normals to move things in and out of each other, and also shadow bias using, whether you're using the front surface or the back surface of objects, they do different things as well. So sometimes we can render using only the back surface of objects, which means the front surface will always get lit. Because only the back surface casts a shadow rather than the front. It's a weird technique though, because not every object has a front and back surface. So not every object has depth in its 3 dimensions. So you could get issues casting shadows from, say, flags or pieces of paper in your scene, depending on what is in your scene. We can also try to make shadow mapping more efficient by saying the frustum for each particular light is fitted specifically to the scene. So we make it as small as possible to the scene, so that what we can do is we can say, we know that there's no scene outside of this frustum, so we only need to render our depth map within a certain frustum. Or you get lights which are right in the middle of the scene and they need a really wide frustum. So different things you can do to try to fit it to the scene exactly. So yeah, that's shadow mapping. The key element of this is to do the depth render from the light's perspective, and then use that depth render to do the comparison between the light's perceived depth of the object and the actual depth of the fragment, to see which one is going to be the receiving the light. Okay, so we're getting pretty close to break time, and I wanted to talk a little bit about CryEngine. That's why I was playing Crysis today, and this is like the kind of story of a graphics engine as it moves through its lifetime. So this was started by 3 brothers. So this is literally talking about people just working out of their basement. And it was able to push the technology well enough that Nvidia asked them to use it as a tech demo. It actually became the Far Cry island. Actually, it wasn't called Far Cry yet, but the island, it was called F-Isle, I think it was called, was an Nvidia tech demo and a benchmarking system. And it was known for those long view distances that we're talking about. So at the time, no one else could do those long view distances. So a lot of games were on indoor environments or had these kind of arbitrary walls or fog in the distance. And so CryEngine kind of opened that up. I mean, one could say that CryEngine opened the door for open world games, in a sense. So they had a deal with Ubisoft early on to do Far Cry, and the Far Cry series is still going now in roughly the same format that it was in 2004. They're in their 6th iteration now. And this is where CryEngine hit the public scene, in a sense, and people started to really take notice of it. First thing was the ability to render these large open environments. So the first Far Cry and pretty much all the Far Cries since have been famous for like um big open vistas, ability to render from very large distances with less pop-in than you get in other engines. Other engines, you get this kind of thing where as you travel in a certain direction, mountains in the distance will just appear. And I'd be like, why couldn't we see them before? It's a huge mountain, right? And so it's weird to have them appear. The CryEngine had less of those problems than other things. After breaking off with Ubisoft, Crytek got involved with EA, so Crytek obviously has a really good um, thinking about which distributors it partners with. So it's got two of the worst distributors in computer games. It got involved with both of them, and then did the Crisis series. So this was from 2007 to 2013. We could say to 2021 because Crisis was remastered just this year. But I think the main development was during this time. And it built up this reputation. There was this meme called "Can It Run Crisis" for being very difficult to run. But it was also known for things like volumetric lighting, volumetric shadows, motion blur. So the idea that you can have those, you know, when they call them those god rays that come down through trees and you can actually see it coming through fog. And so they did a lot of fog effects and stuff like that as well. And they got known for being able to do those things. And they were also doing things like the vegetation and caustics. If you know, caustics is like, if I have this and the light is coming through the water and casting this weird shaped light on the other side of it, they were putting those into games as well. They did tessellation, made good use of the geometry renderer. The geometry shader, which we haven't even talked about in this course. Like I would love to, but like it's hard. There's not much time. Maybe I'll squeeze some time in on Wednesday. And eventually it was bought by Amazon, the CryEngine, and is now the Lumberyard engine, which means you can use it if you want to. I kind of wanted to, I could go for a whole hour just on this slide, right? Talking about things like Lumberyard, Unity, and Unreal is graphics engines you can use where you don't have to build the engine yourself. You use the engine to do things. So the lighting calculations are already in there, specular lighting's already in there, reflections already in there, shadows and all this other stuff, post-processing. It's all just in the engine. All you need to do is tick boxes and it turns on. And that's kind of where game developers are at nowadays, where if you don't want to build a custom engine, if you don't have like a whole programming team of graphics programmers, which I can understand because graphics programmers are rare and expensive, you can use one of these engines instead and get, you know, the expertise of someone else and you license it to use it instead. Anyway, let's go on break. It's 5:03 now. I will come back at 5:08 and we'll start looking at deferred rendering. All right, I'm back. I have edited the slide thanks to Hamish's note that Lumberyard is now Open 3D Engine. So Amazon called it Lumberyard when they first bought it. This Crytek's got a interesting run of companies that they've been involved with. Obviously not doing an ethics pass on any of the companies that they sell their stuff to. Ubisoft, EA, Amazon. I assume that you and your company didn't want your employees to be treated well at all, did you? Anyway. That's quite funny. I didn't think that would be what I'd be seeing when I did a history of Crisis. I thought it was going to be about the tech they did, and then I realized which companies that they worked with. Okay, they worked with Nvidia. I actually don't know whether Nvidia is a good company or not, but yeah, who knows. No, I didn't say anything about YouTube or Google. Google has like a kind of a do no harm policy, but I don't. I haven't really. I'm not looking for trouble just yet. I haven't really gone into what Google does and seen whether they're like 100% ethical in everything they do. I would assume that any company that is turning significant profits probably not super ethical in what they do anyway. But we digress. Let's defer that thinking and talk about deferred rendering. Hamish is saying that Star Citizen uses CryEngine. Yeah, because they're an old enough project that they started on CryEngine 3, I think, and then they went to Lumberyard and now potentially Open 3D. I think it's quite funny. Star Citizen is one of those projects where I was excited about and I backed. I don't know when. I want to say 2000 and something, single digit 2000 and something, so 2003 or something like that, and we were all excited. It was like, hey, Wing Commander's coming back, and then and then it just never happened, and then so many games have just filled the niche that we were looking for that game to fill, and it just never got released. Hamish is asking if I still have my account for Star Citizen. Yeah, I do. I still get the emails from it, but I've never opened it. So anyway, let's continue. Year of Star Citizen release is the year of Linux desktop. Oh, Hamish is asking about. Well, Mark on Mondays might actually start up again after we're finished with graphics. I might actually go back to streaming and like, okay, I'll fire up stuff like Star Citizen and things. I actually have more games now because I just got the Xbox Game Pass because it's cheap, and now I've got heaps of games to check out. But let us defer that conversation and talk about deferred rendering. So let's look at what. I just need to get my face out of the way of my slides. Our current lighting system is something that's called forward rendering. So it's called forward rendering because basically it just goes in order. It goes, okay, find the thing, find the lights that reach the thing, calculate the lighting on the thing. Move on to the next thing. Find the thing, find the lights that reach the thing, calculate the lighting. So it's just adding light as it goes on. The potential downsides to this system is what happens when there's too many lights, what happens when there's too many fragments. So what I'm talking about here is that for every fragment in the scene, we multiply the amount of work we're doing in our fragment shader by the number of lights in the scene. And heaps of those lights aren't even going to hit that fragment. So if you think about a scene that has lights all around it, so let's say we had like multiple directional lights from different directions. So they're hitting everything in the scene from every direction. Any pixel in the scene, any fragment in the scene is going to have a surface normal, which means half of the lights will have no effect on it. So half of the lights will never see it because its surface normal is pointed in the other direction. All of those lights will be part of the calculation, no matter what. So we have that inefficiency there. The other inefficiency that we have is with our camera. Camera's looking into the scene. Camera will see lots and lots of different fragments. Only the fragment closest to the camera will get written to the pixel. All of the fragments behind that final pixel will still get calculated. So whenever we have multiple fragments per pixel, and it's very, very expensive to calculate depth. So we're not going to, it's very expensive to calculate exactly which. Someone's come to say hi, which is good because it's the last week. Come on, chicken. No. She wants me to go that way, so she's yelling at me and asked me to go that way so you don't get to see her. I apologize. Anyway, when we have these pixels, they're all behind each other, and we're just going to calculate lighting on all of them, and we're going to lose all that work because the pixel at the front is the one that's going to cover up all the others. So this, in a sense, is an inefficient algorithm. Every time there's multiple lights in the scene, anytime the scene is of a reasonable complexity, with lots of things in front and behind each other. You looked at the crisis there. There's all these trees, there's rocks, and there's mountains, and there's buildings and stuff like that. There's a whole lot of geometry that's not visible. We're going to spend time calculating lighting on all of that geometry. So what we're ending up with is roughly the amount of work is the order of the lights multiplied by the number of fragments. So number of fragments, and for every fragment, we use all of the lights on every fragment. So that's our calculation there. So it's a reasonably simple kind of time complexity analysis of that. Like, I'm not going to go into too much detail, but you can see that this is a problem. It scales very badly on the number of lights. So the number of fragments, we don't have a great deal of leeway there. Like, we're kind of going to have to pass every fragment, but every light to every fragment, then just like, it ends up taking a lot more time than it should. So the solution that we have to this is something that started happening in real-time games. Who started deferred rendering? I think it was like, there's this really obscure Xbox game. I think it was the Shrek Xbox game was one of the first games to use deferred rendering. So it was a really good testbed for it, because like, officially licensed game like that, it's not really going to go do that well, but it did manage to do this deferred rendering. I'm not sure why they did it, other than they had people in the team who were interested in the new technology and wanted to try it out. The trick behind this, deferred rendering, the clue is in its name. It does not, it's also called deferred lighting sometimes. It doesn't do the lighting until after a fragment has been decided and confirmed to be visible. So what we do is we look at our scene, and we look at all the geometry in our scene, and we say which thing's at the front after we've calculated all the others. We see which one's at the front, and only then do we do the lighting pass on it. So that already seems reasonable. You know, when you think about that, what we could do is we separate the work that our fragment shader does into, say, two passes, in a sense. The first pass is just to figure out which things are actually appearing on the screen. So which fragments are pixels. Which fragments are never going to be pixels because they've been covered up. We will never calculate lighting on those. We only calculate lighting on the very front fragment. So this takes away the issue of having a lot of fragments in our scene calculate lighting. So this takes away that multiplication of fragments times lights, because we're taking out a lot of the fragments that are in the scene. However, if we don't know which fragment is going to be the one that's lit, that means we're going to have to save the data for all the fragments. So again, frame buffers, rendering to textures, frame buffers. We're going to render out to frame buffers all of the information that we need to do our lighting calculations. So you think about what we need for our lighting calculations. We need fragment positions, we need surface normals, we need diffuse colors, we need specular components. We need to know what our textures are so we can sample them and stuff like that. We don't necessarily need the textures. We can probably sample them and then store them in this new frame buffer. So the cool thing about that then is that we will be calculating lighting per pixel, not lighting per fragment. So just this part of it reduces us to, instead of the order of lights multiplied by fragments, we have the order of lights multiplied by pixels, which is nice because fragments is an open-ended number of objects, whereas pixels is a very fixed number, and we will never have more pixels than we have in the window or screen that we're rendering into. So that's a nice limiting factor. The next thing that we do with deferred rendering is we start to treat our lights not as these universal things that access everything in our scene. Our directional lights are still probably going to be that, but things like our point lights. Hello? What is it? Someone doesn't like deferred rendering. Someone would prefer cuddles than deferred rendering. So, with our lights, we are now going to treat our lights a little bit like their geometry, rather than treating them like they're this abstract object that affects our scene. And when we were working with point lights, we were talking a little bit about the idea of having, say, attenuation on point lights. So if you have an attenuation on point light, it's bright when it's close to it, and the further away you get from the light, the less light is involved. Look at that grumpy face. So you could do something where you say, let's detect the distance between the light and an object. And we say, if it's further away than a particular distance from the light, then the light doesn't affect it and we won't have to use our lighting calculation on it. So we'll go into that in detail. But what we're actually going to be doing is treating our lights as if they are geometric shapes. So geometric shapes that we have been working with in graphics and we already know how to render. We're going to use them to decide what our light can and can't hit. And the beauty of that is that's going to significantly reduce which pixels are going to be affected by the light. So it's no longer a multiplicative relationship between all of the pixels on the screen and all the lights on the screen. It's that the lights are going to choose only a constant number of pixels that they're going to affect, and we're going to get to this kind of time complexity scale where we're in the order of the number of lights plus the number of pixels, rather than the number of lights multiplied by the number of fragments. So most of what deferred rendering is really flipping around everything that we're doing with our lighting algorithm to make it significantly more efficient than it would otherwise be. All right, I'm just gonna put the camera back up to me. Had a little taste of chicken, which is nice. Okay, so how are we going to do this deferred rendering? So I talked about a little bit about what it is and what makes it good, but what we need to do is go through the details of exactly how to make this work. So the first thing that we're going to do our lighting nearly like a post-processing thing. So in post-processing, what we would be doing is we'd be rendering our scene first, and then we would take the frame buffer that we'd rendered to and we do something to that frame buffer. So if I want to do like a blur or something like that, I would do a kernel and I would access the other pixels around it that had been rendered and say, okay, given those other pixels, this is the final color. So the post-processing happens after the render pass. So deferred rendering does this kind of thing where it actually takes a bunch of stuff out of the first render pass and does that afterwards. And the first render pass is actually going to be only geometry and no lighting, which means the first render pass actually turns very, very cheap. It's nearly just a data gathering pass that will determine which fragment is at the front of the scene using just normal depth buffer based rendering, but also it will store some information that will be needed later, because if we're going to push our lighting out of our first pass, we need all the information for the lighting. And then after that, we'll go through each of the pixels and we'll do the lighting pass, lighting each pixel. It changes a little bit when we do the lighting as volumes, but I want to break this up into two kind of steps. So the first thing we're going to do is get ourselves doing lighting per pixel rather than lighting per fragment, and then we'll add the light volumes in, and we'll talk about lighting per light object as well instead. Okay, so here is an image of the geometry pass, sometimes shortened to G pass, stores things in the G buffer. I guess geometry, it's a 4-syllable word. People didn't like the 4-syllable word, so they bring it down to a single letter. So what we get is 4 buffers. And they're basically standard frame buffers, because you can store just RGB information in these things and you'll get enough information to be able to do everything you need. So the 4 things that we're going to be storing in these separate buffers are going to be the all the pieces of information we need in our standard Blindfong lighting algorithm. So we're not actually changing the lighting algorithm. We're still using the same way of calculating illumination and things like that. We're just changing where it's done. So what we do first is we render our scene, and the only things we do when we render our scene is we sample the fragment position, the surface normal, the diffuse texture, and the specular texture. I mean, you can do other things if you need to, but this is the standard thing that will do everything that we need for the Blinfong. With these, instead of processing them, instead of using them and punching them into the lighting equation, we're just going to save them. So, see, this fragment in the top left corner has saved 0 information on either of these because there's no objects. But this pixel here has been done at least twice. Like, I'm just going to say at least twice because I can see there's one of these bags behind and this one bag in front. So 2 fragments were calculated here. The one that was in front of the other, depending on which order it was done, we don't know which order it was done, but the one that was in front is the one that has its final data written in that particular texel in these G buffers. Actually, we tend to call it one G buffer that has 4 the 4 of the standard buffers in it. So we know where the position is. So this is just RGB color based on the position in the scene. So if you look at this, R is X, green is Y, and blue is Z. So as things are to the right and in front of us, then they get like the red and the blue. Things that are high in the scene get green, high and forward. So high and to the left get a cyan because that's the mix of the blue and the green. So you can see how this is a color representation of the fragment position in the scene. So this is more than just its position in that screen. This is its position. These are actually like the world coordinates of the fragment position. The normals, you can see this looks a little bit like what we're looking at with normal maps. This is just the direction that each of those fragments is aiming. I should say pixels here because now it's pixels in a sense. So the object in each of those pixels is aiming in a certain direction. Here we've sampled from the texture and colored each pixel for whatever color was going to come off the diffuse texture for these objects. So we've just got repeated objects here, which makes it okay. And then we've got a specular map on each of these. So it looks like the little axe head on this, looks like a old school camping backpack. The axe head has a lot of specular reflections. The buckles have specular reflections. A lot of the fabric has no specular and things like that. So what we've done here is we've recorded all this information. So now if I go in and I sample a particular coordinate, so a UV coordinate in the position, I can get its fragment position, and then I can sample here and get its normal surface normal, sample here, get its texture color, sample here and get its specularity. So this is nice. This is all the information that I need in order to do a lighting pass. And I've stored it now in this buffer. And I have replaced any of the information that was for fragments that I couldn't see. So if I can't see the fragment, it has no information here. So this is all being rendered from the main camera's perspective. So this does not make a scene yet, but this is all the information in separate pieces that we're going to use to light the scene. Next thing we do is we do our lighting pass, which is different from our normal lighting. So normal lighting would be like, look at each fragment, and this is going to be like, per object. We would look at the fragments that the objects influence, and then we do a lighting pass on each fragment. Instead, this time what we're going to do is we go through the pixels, and for each pixel, we just pick up the data from the G buffer. Because we've got a 1-to-1 ratio, the G buffer is the size of our screen. So the G buffer is basically in pixels now. And we go in there and we sample that pixel and we say, okay, sampling that pixel in these 4 buffers, I get the information I need and I just do my Blinfong lighting calculation. So it's actually reasonably simple when you do it like that. All we're doing is we're saying 1 pass for geometry. And so that picks up, the G pass picks up all the information, and only after the G pass has confirmed which fragments are actually going to be pixels, then we do the lighting only on the pixels that exist. So it's a nice kind of system. And so let's think about how much of that has helped us at this point. The more overlapping fragments we have in our scene, the better this system is. So this is like, I haven't even talked about light volumes or anything yet. That's the second part of this. But if we're talking about just deferring our lighting until our post-processing step, we have probably significantly reduced the number of fragments we needed to light. Even in a scene as simple as this, we're in the order of like, maybe halving the number of fragments we had to calculate lighting on, because like say this one's only got the front half, like the top half, and this one's got even less of it. So heaps of these have fragments that would otherwise have had lighting and don't have lighting here. So that's nice, right? So we're now down to like a kind of a constant, in a sense, that the number of pixels is a constant number, and we know that we will always do that many lighting calculations. So we don't have have an idea of a scene where if there's lots of depth, lots of like, you know, those dense vegetation, all the trees and all those leaves and stuff like that, we don't have any of those issues where we would have to light everything at the back, everything in the middle, everything in the front. We're only lighting the things that we can see. So this is again one of the things that made the massive draw distance of something like CryEngine possible, because we can have all these other fragments and we're just going to ignore them, you know, because they're covered up by something close by, and we won't have to spend so much time lighting them. This isn't perfect though, right? So we have deferred lighting, but we haven't necessarily gotten to the point where I said we were going to get to, because we're still applying every light to every fragment. I should say pixel here, actually. You know what? Because we're not applying light to every fragment. We're only applying light to the fragments that are closest to the camera. But we are now still applying lights that might not have an effect. I'm just going to change this as well. Because at this point we are actually in pixels rather than fragments. In a sense. I want to separate it as in chosen fragments. It's not necessarily pixels yet, but it's like the chosen fragment, which is basically a 1-to-1 ratio with the pixels. Okay, so we now need a technique that is going to limit to us which lights apply to which pixels. So this is the idea I said earlier, to render the lights as if they're volumes. So one way we can go about this. This is the theoretical idea here. The theoretical idea is that we could calculate where lights have an effect. So what we do is we take, like, this is mainly for our point lights, right? Our directional lights kind of hitting the whole scene anyway, so you're probably going to want to render the whole scene with directional lights. But a lot of our point lights are small lights. I go back to Little Lamp, who has been my friend in this course where we talked about this with attenuation. It's lighting me here. Oh, it's got some nice bloom here. We talked about bloom, right? But it's not lighting the back of the room there. So if I was to calculate this light against the back of the room there, that's kind of a waste. That's a waste of our resources. If you look at it, the back of the room is not really changing. It's changing because my camera is trying to deal with the extra light in the scene, so it's doing auto exposure and stuff. But this light has a limited sphere of influence. So what we could do if we want to, this isn't that hard to do, is where what we do is we say for every point light in our scene, every point light has a certain amount of attenuation. So a certain amount of distance from which it is insignificant. It's not ever completely non-existent, but insignificant for our lighting calculations. We won't really be able to tell the difference. So we could take a radius for our point lights. We could take a cone shape for our spotlights. I mean, like spotlight, we can just measure the angle and the radius. And what we can do is go into our GPU and say, if this light is further away than its radius. So this light has a radius. Let's say it has a radius of 1 meter. Every object that's more than 1 meter away will not be rendered with this light. So this light won't... I think I'm breaking the lampshade. Everything that's more than a meter away from that light will not receive its light as part of the light calculation. And the bigger light in my room, which isn't even on at the moment, will have a larger radius. So we could do that if we want to. And then what we say is, like, we put if statements, if else statements, we put branching code into our shader saying we do use this light or we don't use this light. And here is where we get to really like a kind of a hardware specific issue. Here is that generally the way that our GPUs work is we have like this sort of massive parallelization of our GPUs, like 1,000 processing cores, where our CPUs are at, I don't know, 8 to 16 kind of cores, depending on how you look at it and how much money you've thrown at your CPU. But the order of magnitude of the parallelism is very different. But in order to do that kind of large scale parallelization that the GPU is capable of doing, what generally will happen with the GPU is that its parallel cores will run in lockstep, which means what we'll do is we'll feed in information from multiple fragments at a time, and then we'll run the same code on all those fragments. So it'll be like, okay, do line 1. Now everyone do line 2. Now everyone do line 3. It's not that simple, right? These are instructions, not lines, but you know where I'm getting at here. It'll run your shader code, the same shader code on everything. So the downside of putting branching code into shaders, so branching code into your fragment shader, for example, is that all of your processing cores are going to run all forks of the branching. So if you do an if else and you go, I'm going to be smart about this because I've done all my programming on CPUs in advance, is that I put the easy thing first. So I do if this, and then I do the easy thing. Otherwise, I do the hard thing. So what happens is I've got an escape. If I take the short branch, I will never read or look at the difficult code that comes later. But if you have 1,000 cores all going at the same time, and one of them hits the other branch, then everyone is waiting while that thing goes through the other branch until that thing has finished the complicated code, and then you go, okay, everyone's finished this if else, now we'll go on to the next line of code afterwards. So generally that's what our GPUs are doing with our shaders. So the problem then is, if I say, everybody, only calculate this if you're within 1 meter of this. And so we look at all of these fragments, and then one of the fragments is over there, which is like 2-3 meters away. So most of the fragments over there 2-3 meters away, and one of them is here. So one of them's here where I am, and it says, okay, we're going to run this code. And it's like the whole GPU goes, okay, we're all running this code. And all the other fragments back there are saying, okay, we're going to ignore it, but we do have to go through it. But we're ignoring it because we're on the other side of this if statement. So even though they're ignoring it, it doesn't matter. They're still taking all the time it would take to process it because they're all in lockstep. So it doesn't really help us. We can't put in our shader a detection for the radius of the point lights to remove some of the point lights from our lighting equation, because it doesn't matter, because we're going to go through all of the code. We're going to go through both sides of the if-else statement and run it all. So the idea that we could just fix this at a software level in terms of like what we're writing in our shaders to say, don't calculate that lighting equation, calculate this lighting equation, remove some of the lights from this lighting equation, which would remove our time complexity for things, it won't actually help. We'll still be stuck in a situation where every single light applies to every single pixel, because there's no way to separate that code and have it not run in the parallelization of our GPUs. So it's a little awkward, right? Because our hardware gives us so much. Our hardware gives us this amazing capability to do this large-scale parallelization, but it doesn't allow us to have independent processing cores. And I think that is really one of the fundamental differences between a CPU and a GPU. Whereas there's no way we're going to have like all 8 cores of our CPU running the same code at the same time. And be like, why would we do that? The whole point of having multi-threading is to have some threads on some CPUs dedicated to something, other parts of the CPU dedicated to something else. I don't want everything in my computer to stop running when I move my mouse, because I don't like, I want the mouse to be controlled by some part of my CPU and for it to process the data and to figure out where the cursor goes. And I don't want other things in my computer to have to wait for that to finish before they can continue going. But unfortunately, that's where our GPU is at. So if our GPU is in that situation where it is going to calculate every light, regardless of if we tried to turn some lights on and off for particular pixels, there may be another way to do this. So what we can do instead is we can render each light individually. So we can take turns and we go, okay, do this light, then do this light, then do this light. And then if we have a good way of determining which pixels each of those lights affect, we can significantly reduce the multiplication of lights to pixels in the scene. And this is where we get to the idea of lighting volumes. So what we're going to do now is render lights as if they're geometry. And again, this is the same kind of thing that I was talking about before. Let's lean in on the capabilities that we have available on our graphics card. So instead of trying to fight the hardware, why don't we work with the hardware? The hardware's like, oh, I do geometry rendering. I do geometry rendering fast. I do it really fast and really easy. So we're like, okay, if you got that, but you don't like us flicking on and off lights, you don't like us doing branching code in the shaders, we'll do this whole thing like it's geometry instead. I just love this idea because like the people that came up with this stuff, I should have really looked up everyone who, so I reel off the list of names that people did this research. But I think some of them are going to be familiar names. It might be people like Catmull Fong and what's his name again? The Doom and Quest. I can't believe I've forgotten. Oh, Carmack. That's it. It could have been some of those names. I'm not sure though. They're not the only people in graphics. But what we do is we go into the lighting pass, and instead of doing lighting in the lighting pass, we do geometry in the lighting pass. So what we do is we render each of the lights like it is an object. So here they're using spheres. You don't have to use spheres. You can actually use much simpler objects like cubes. Cubes are not as good as spheres because you'll pick up more fragments. But they have less geometry. So it's a trade-off. Generally, though, you probably want to reduce the number of fragments because that's where all of the expensive work happens. So we do this really funny thing where we go, okay, this light, we render this light as a piece of geometry. And the sphere that is representing this particular light is based on its attenuation radius. So we're saying that on the edges of this sphere, we're saying that once we get out to these edges, there's not enough light for this to count, so we won't render anything more than that. So what we do is we render this thing using our G buffer. And the best thing about this is our graphics card is very, very good at deciding which pixels should appear given this shape of this geometry. So the stuff that our graphics card is doing to be able to determine based on vertice positions, model view, projection transforms and stuff like that, to determine if there's a sphere that exists in our scene at a particular world position, which pixels it actually affects, we've already got that whole pipeline in place, right? We've already done all that work. We did that work in the first half of the course. But instead, now what we're saying is, if we invoke the fragment shader, so if this object says the fragment shader must run on these pixels, only the pixels where it appears, it would not run, this object will not run the fragment shader over here, will only run the fragment shader here. When it does run that fragment shader, let's take all the information from the G buffer that samples from the particular pixels that we're at, and then we'll calculate this light with these pixels. So the cool thing is now each light has a constant number of pixels that it will do, and it could actually be quite a small number of pixels if you put its sphere of influence very far away. We are no longer multiplying the effects on multiple lights on multiple objects, unless these light volumes are all just massive and they take up the whole screen. But the trick is, what we're going to do is have a lot of small localized lights as all these separate little objects in our scene, and each one's only going to calculate its lighting on the pixels that it can affect. And if two lights overlap each other, they both affect those pixels, then in each of their passes they'll add more color to the final pixel there. So this is really cool here, because what we're getting is, instead of, like, you could still get into a multiplicative situation if all of these spheres of influence are just covering up the entire screen, right? We can still make this inefficient if we try hard enough. But the majority of the time, when all of these lights have their own little local area, they will only be calculated in their own little local area. And that incredibly increases the efficiency of what we're doing with our lighting. So, what we're getting out of this when we do the light volumes as rendering, so what we're doing is a lighting pass that does a geometry render. And also, by the way, this isn't multiple passes with multiple pieces of geometry. You know how like when we have geometry, we're going to render all the geometry, depending, even things that are behind and in front. We will still render each of the lights, even if they're overlapping, but each one just adds to the color of something. So this isn't a situation where we do multiple passes. It's like another render of the scene, and this time it's rendering just these spheres. And instead of rendering these spheres with like the lighting calculation for their surface, what we're doing is we're rendering them for the lighting calculation out of the G buffer instead. So we end up with a situation where each light is looking at a constant number of pixels that it will do, not a multiplication of all of the fragments. So it's not even all the fragments it can see, because we've already deferred the rendering to choose only certain fragments that are in the G buffer. But now what we're doing is we're saying that with these, say, spheres or cubes, or you can even use like sort of trapezoidal, like a frustum kind of thing for spotlights and things like that. We can now render many less lights for each fragment, each visible fragment in the scene. The downside, I guess, is it does add multiple passes. So we've got to do our geometry pass, but that's actually pretty simple. The G pass is just collecting data and writing it to memory. So yes, we're going to use a bit more memory. There's other things we do need to think about, however, when we're doing deferred rendering with, say, the spheres of light like this, is if you walk inside one, can you still see it? So you do need to fiddle around with your culling settings to make this work, in that if you're inside something, then maybe you want to render back faces. So the back face is the internal surface of that sphere. So if you're inside it, you can still see where the sphere has its influence, has its sphere of influence, because you can see the inside face of it if you're inside it. However, if you have your culling set up, culling is like removing the polygons that you can't see. If you have that set up to render the front and the back faces of everything, then you'll render every light twice. So you've got to be a little bit careful about how you do this. But that's just an optimization. It's not something that I want to go too deep into, but it's a potential issue. I think the bigger issue is once you're inside the sphere, it is no longer lighting things if it doesn't turn up in this geometry render pass. So that's one of the little issues to think about with deferred rendering. So a little analysis of deferred rendering. Here's an image. I couldn't actually find this particular person's original blog on this. I think it may have been lost to history. But this is a photo that was used in Learn OpenGL, and other people have referenced this person, but I can't find their actual work. I think there were some papers and things, but like I was looking for the blog that had these photos. So what we're looking at is a scene here with a whole bunch of these textured balls in the scene, and what looks like several hundred lights. And this is totally doable with deferred rendering, because when we're looking at forward rendering, we're looking at multiplying lights per objects, and we'd have to do this for all of these. I'd assume that a scene like this would grind to a halt. Whereas when we're deferring our rendering, so for the first part, a lot of the fragments of these balls are not going to get a lighting pass done on them at all, and then a lot of the lights are only going to affect small areas in this scene. So we're going to be able to deal with these hundreds of lights, because what we're going to be doing is just rendering them like they're bits of geometry. And we already know we can render this much geometry. So it's not exactly, but it's like we've only doubled the amount of work we do by adding hundreds of lights. And it really didn't matter if we had hundreds of lights, we still only doubled the amount of work that we did, rather than like, because it's like a geometry pass and a lighting pass, which is like a geometry pass. As opposed to, if you try this with, say, what you did for tutorials and assignment 2, and you just put like a few hundred different colored point lights in your scene, let me know what happens. I'd be interested to know what kind of frame rates you end up with if you do it in a standard forward rendering pass. So you're going to need to do a loop inside your shader that loops through all sort of 300 of your lights, accesses their information, applies their lighting, adds it to the object, then go to another one, do the calculation, add it to the object again, all the way through your shader. It'd be interesting to see how much your graphics cards can handle. Modern graphics cards might actually get up to, I don't know, 30 or 40 lights before they start to grind to a halt. But even in the simple code that we've been writing, like not fully featured rendering, once you get up to a certain number of lights, graphics card's not really capable of doing it. So deferred rendering is really good. Good for multiple lights, and better the more fragments are overlapping each other, because it just really removes that problem from us. Downsides to deferred rendering that we do need to think about sometimes is, yes, we're doing extra render passes, but honestly, that's not that big a deal. Like, this is only a negative, the extra render passes, if you have, say, only one light in the scene and it's a really flat scene without things in front of each other. Because even with only one light in the scene but lots of things in front of each other, deferred rendering is still an advantage. I guess a genuine downside is memory usage, because we're looking at minimum 4 frame buffers. We're looking at the memory usage to store the geometry that the lighting is using, but honestly, that's so little memory. Because when you think about it, like, this is over the top. These spheres are way over the top. Like, I'd be happy to use really, really low resolution spheres that are just a little bit bigger than the space they need to be. And you'd use very little memory for these. So, you know, the geometry of a sphere with nothing else, and especially a low poly sphere, is going to render really quickly, and not take up too much memory. But still, I think it's the G buffer is really the memory, having four frame buffers that you're storing. But again, I think that this is the classic trade-off between processing time and memory usage, that we can use a little bit of extra memory to reduce our processing time. And in real-time situations, so like graphics and games is not the only real-time situation. When you've got like monitoring systems, self-driving cars, all that kind of stuff, you need real-time systems. The time it takes to work in those systems is usually far more important than the amount of memory. So we'll usually say, look, let's just use as much memory as we can so that we're using less processing power. The other thing that's interesting though is that if we're doing our lighting per pixel and not doing a pass where we say, here is our object, here is all its vertices. Now, using the verts and the fragment shader and the model view projection, we will tell exactly where these fragments are in our frame buffer, and we will write to our frame buffer just where this object is. If we're going to do that, we can actually put custom shader code in for each object. Deferred rendering takes out the capability to do that. So it's very hard to deal with any kind of specific weirdness or anything that's going on in a particular object, because you're looking at a pixel and you're saying, I just light this pixel. There's no information in the G buffer that says, oh, careful, this object is of this particular type. Say it's a transparent object and it must be rendered after other objects. We can't just throw them into the scene and hope they work. So what often happens with this, I didn't write another slide about it. But what often happens with specific objects that need to be rendered in a certain order. So reflective objects, transparent objects, and other things like that, they will have to have a separate pass outside of the deferred renderer. So what we would do is we'd do our full deferred rendered scene, and then we would say, all right, now we add our transparent objects in afterwards. And if our transparent objects happen to be in front or behind other objects, they will be able to see through to the objects behind, but not the ones in front. So you have to kind of put them into this scene and make sure that your deferred renderer is writing its depth buffer calculations. So your deferred renderer is definitely doing depth buffer work, because otherwise you don't get the idea of, say, this normal map is in front of the normals from the other fragments. So it does have depth buffer information, but it hasn't written it out in this one that we've looked at here. But you could add another buffer that writes out your depth buffer. And then you'll have a depth buffer to do things like a transparency pass, and you say, okay, there's a transparent window. It is behind these objects, but in front of these objects. So it will take the colors from the objects that it's in front of, and then bring them into the blend of the transparency. But yeah, it just means that the deferred rendering can only do certain things. And there's certain types of objects that require us to do a separate forward rendering pass that we mix in with the deferred rendering. Usually after the deferred rendering. There's not a lot of things that would happen beforehand. I think, unless we're looking at reflections, sometimes we may render the reflection object so that its texture is available for the deferred rendering pass that happens afterwards. That's really difficult because you kind of want to do a lighting pass on the render from the reflected object. So maybe you're doing 2 deferred rendering passes, one from the object's perspective and then one from the main camera's perspective. I haven't really looked into that too closely, but it could be a thing. Okay. So here we are at the end of what I am expecting to be the 2 hardest techniques that I've taught you in this course. So I said that at the very beginning of the course, I didn't know how my plan was going to shake out, whether some things were going to be taught faster than others, but the thing that I wanted to reach at the end of the course was deferred rendering. So that was this goal that I had, and here we are pretty much at the end of the course, and I was able to at least show it to you, even if we don't really have time in tutorials to do it. However, if you look at the technique and you break it down into the idea of render to frame buffers, then do post-processing on those frame buffers to go to the main frame buffer afterwards, it's just a more complicated form of things like a black and white filter or a or a blur filter or something like that, you know. So it is possible, and it's only an extension of what we've learned. It's not like a brand new technique or anything like that. Same with shadow mapping. So going back over what we've covered today, shadow mapping allowed us to render from the perspective of the light. Rendering the perspective of the light, just a depth render from the perspective of the light, will allow us to tell what the light can reach. So it's not really what the light can see, because the light doesn't really see anything, but we're figuring out what the light can reach by rendering from its perspective. And then that will allow us, when we transform back and forth between the light's perspective and the main camera's perspective, it will give us the ability to detect whether the fragment from our main camera is actually going to receive the light from the light source. Gets a bit fiddly the more lights you try to do this with at a time, and it has fiddliness of just a whole series of different possible sampling issues. And so you can look that up, look at the more detail in that if you want to. And then looking at deferred rendering, one of the beautiful things about deferred rendering is it takes this massively multiplicative lighting system that we have, and it removes most of the multipliers out of that system. So we take it from fragments to pixels. So we go from a multiplicative number to a constant number, and we take it from all lights affecting all pixels, or if worse, all lights affecting all fragments, down to lights only affecting certain fragments, and being able to do it in a render pass that is more hardware friendly for the way our hardware will actually work with geometry rather than multiplicative lighting in a sense. All right, I'm on time for once. I'm going to wrap it up there. Let me go into break mode, and I'll come back in a second and answer any questions people might have about these topics. I understand if you have questions, these topics are pretty full on, but there is a lot of reference material for both of these, especially if you want to. You can go into the Learn OpenGL and look up, like, there's even code samples there. I don't think that code works exactly in our setup, but it shouldn't be that hard if you really wanted to do these things to convert them. All right, I will be back in a second and answer any questions people have. back. Did we have any questions? I don't know if I don't know if the talk through of everything was useful enough to get an idea about how these techniques work. I do understand people probably want to try to put this stuff into practice at some point. But also should point out that it's not entirely necessary to do so. So if you look at how many marks I've assigned to these things in the course, they're really just, have you already kind of done everything else in the course? Here's like a little bit more. So it's kind of like if you've already got your HD and you're trying to like max out the course, then you can go in and do both of these techniques. And that's really that's only for that case, for people who are in that situation. Anyone else who is like happy to do well in a course but not like max out the entire course, which I think must be like, there's very few people who are trying to max out a course and get 100 in it. You could look at one of these techniques, or even none of these techniques, and do other things instead, like normal post-processing and things like that. Yeah. Commerce is asking, I'm curious, what do you expect an assignment to have for it to pass assignment 3? There is no passing assignment 3. There is no notion of a pass for assignment 3, in the same way that there was no notion of a pass for assignments 1 or 2 either. So what I'm expecting is a student that wants a pass for the entire course will probably do about, I don't know, I was thinking like 30-40% of assignment 3. Because I'm expecting someone who was expecting to pass the course, so the average marks for the assignments, in a sense. So this is the way I've scaled the courses. The average mark for the first assignment is about 90%. So we actually have the data on that, because that's marks. The average mark is about 90%, which is what I intended. I was basically saying that if you're going to be okay to continue in this course, you should basically have gotten 100% in the first assignment. And that's why it was before the like the submission was before the the census date. We didn't manage to get all the marking done before the census date, but I think people kind of on submission, for assignment 1 especially, you probably already knew close to what mark you were going to get. Assignment 2 was still pitched so that people would get a higher mark in assignment 2 than they'd probably expect to get for the course. So I'm expecting the marks assignment 2 to be around 70% average or something, 70-80% average. I don't know exactly, but you'll note that for assignments 1 and assignment 2, you probably got away with copy pasting a lot of stuff from the tutorials. Assignment 1 was literally like, it wasn't even really testing graphics as such. It was testing whether you can get your computer set up to do graphics properly. That was the majority of it. It's like, I gave like something like 50% of the assignment to like get it running, right? Someone was asking about, oh right, I read the answer without the question, so it was like, yeah, someone was asking about assignment 2 marks, and I did send out a notice today, but that notice only went out about 4 hours ago, I think. It was about 2 p.m. I think it was 2 p.m. or maybe it was 3 p.m. So maybe it was only 3 hours ago. So yeah, yeah. So we're starting marking on assignment 2 in 3 days. I think it is. Is it 3 days when the we've got a 5-day late penalty, which means Friday through to Wednesday. So we're starting marking probably about 3 days, on about Thursday. But I'm not going to make the tutors get me marks back within like 2 or 3 days. I'm going to give them a little bit more time to mark. And so we're hoping that we'll have a full release of assignment 2 marks mid next week. So you should actually know exactly where you sit in the course. And how much of assignment 3 you need. If you feel like you have a drastic need for something in assignment 3, then you'll know which bits to do. So you'll note that if you look carefully through the criteria of assignment 3, the lowest possible mark in assignment 3, if you write a pitch and you do something interesting for the subjective marks, and you only use stuff that you've completed in tutorials, so this is assuming that you've completed all tutorials, the floor of the marks for assignment 3, the lowest possible marks, is about 25%. So you're kind of guaranteed that 25%, and then you build on that further if you want more. So it's kind of like if you look at how many marks that you've gotten in the course so far, and then you do that easy part of assignment 3, the 25%, then you can add up your marks and you go, okay, am I passing the course now or not? Or am I reaching whatever goal in this course I want to? So if your goal is an HD, then get ready to do a whole lot of work, right? Because no one gets HDs for free. But if your goal is to pass the course, you can be like, okay, what's my minimum necessary? So let's say the marks are average. Someone's got close to 20 marks for assignment 1. They've got roughly 25 to 30 marks for assignment 2. That means they've already passed the course. So anything they do in assignment 3 is bonus, or you figure out what your deficit is to get to 50, and you go, all right, where are the easy bits in assignment 3? And each of the sections in assignment 3 is kind of goes from easy to harder. So you can do like the post-processing, like the first bit of the post-processing. The first couple of bits of post-processing are quite easy to do, especially because there's going to be tutorial doing the setup for post-processing this week. And other things like, oh yeah, there's a massive freebie in there. There's marks assigned to Blingfong lighting. And we've literally implemented that for you. So there's a massive freebie. You go, okay, there's the algorithm. It's in my tutorial code. I'm going to take that algorithm. I'm going to put that into my shaders and apply it to whatever I'm doing in my scene. So there's a few things in there. There's also a design pitch thing, which we did back in week 5, where we were talking about settings, game ideas in a sense, and the technology necessary to do them. Now, you don't have to come up with a good idea for a game for that one. You just have to, you could come up with a really generic, boring idea for a game. It's like, this game is just like Call of Duty, but it's got a different name. Oh, thanks, Battlefield. Well done. See, we've already proven that makes millions of dollars. So all you need to do then is say, okay, this is the technology that we would use to do that. Which pieces of graphics technology do I need to render this effectively? And the good thing about that is you should have a decent knowledge about all the different things that we might need without needing to know how to implement them. So that 5% that I put in for the design pitch, I won't call it a freebie. You still have to think, but you don't have to implement anything. It's probably going to be quicker to get 5% of the marks of the assignment there than it is to look at, say, the final part of the deferred rendering part of the assignment and go, ooh, that's where I want my 5%, you know? So there's a difference between 5% that I'm giving to people who need to pass the course and 5% that I'm putting there as a hanging fruit for people who have already gotten all of the other marks in the course and they want the hardest possible thing to push themselves up to like 100. You can see how different parts of the criteria, even though they have the same amount of marks, they're really for a different, like, for a different position, a different perspective of where you're looking at where you want to get marks. So what people say, Commerce thinks you've bombed assignment 2, so you need to do a lot of assignment 3. See how you go, you don't know yet. Yeah. Well, wait until you get your assignment 2 marks, but also definitely look for the marks that are like you can read the spec. Like, I'm not necessarily going to do this for you, but you could read the spec and you can see, actually kind of have already, you can see where the free marks are. And there's just less free marks. So like assignment 1, if I consider free marks, like the entire assignment 1 was free marks. Assignment 1 I consider to be your participation mark for the course. And the way that I balance this, because I don't really want to fail too many people, right? And so what I was doing was making sure that the average mark was 20 higher. The average mark should not be 50 in a course. I don't want to fail 50% of people in the course. And so the assignment 1 was a lot of freebie marks, but you could actually consider that there's nearly as many free marks in assignment 3 as there are in assignment 1, because about 20-30% of assignment 3 is free marks, and assignment 3 is worth twice as much as assignment 1. So there's this kind of balance there where I'm trying to make sure that, you know, this isn't a course I'm trying to fail people in. So some people will fail because that's how courses work. There's 300 people, so there's no possibility that every single one of 300 people in this course has put in a decent amount of effort. Like, things happen. Your life gets busy, you have to do other things, stuff happens. So, you know, I failed courses as well. It's not that big a deal. It's like I ran out of time, I didn't do everything, and I refused to cheat, so I failed. Actually, that's a bad way to say that. If you cheat, you do worse than failing. You get kicked out of the uni and stuff like that. So, yeah. So I guess there are going to be people who are going to fall below the line, and that's unfortunate, but that happens. But it doesn't mean that everything's over. It might mean that they can come back and do it again if they're interested in it, or they can say, look, I may have failed the course, but I got a lot out of it. I got educated and things like that, and I'll go get a pass in a different course instead. However, what I'm hoping for is the way I've designed the assignments puts us on a good curve where the average mark is somewhere around 65 to 70. And some people will get marks in the 90s, but they're very hard to get, as they should be. And some people might fail the course, but that should also be hard to do. So let's see where the balance is there. Who knows? Hexus is laughing at me dividing the first-person shooter community by putting Call of Duty and Battlefield against each other. I think that's just really funny because like those two games have just been treading the same ground as each other for such a long time. Cineo, can design pitching be nothing to do with our actual work? Yeah, if you need to. So one thing that I put in the example design pitch that I put in there was like, here's a game and it does this stuff. I think it needs this and I haven't done it. So I made sure I put that line in there saying this is going to need a deferred renderer, but I haven't implemented it. So whether your assignment relates to your design pitch or not, it's better if your design pitch is exactly what your assignment is. So you go, this is what we intend. And then you go through it, and then the last thing you do. So this is why the design pitch is at the beginning and the subjective mark thing is at the end. So the subjective mark is, this is what I actually did, and I would like some marks because it looks cool, you know. Whereas the design pitch is like, here is an idea of what we could do, and here's the tech that we would need to do it. Whether or not this stuff is implemented is not really part of the design. And also, if you design something at the beginning, that's not how it's going to end up. Look at Overwatch, for example. It was designed as an MMO, and then turned into a team-based shooter by the time it was released. It used to be this project called Titan in Blizzard. So, you know, your design pitch could be that different. And I'm accepting of that because that's like reflecting of reality. It doesn't have to, like, your design pitch does not have to be reflected in your implementation. It's better if you do your design pitch and then you try to implement things that will help it, you know, because that kind of makes sense. But there's no limitation like that. So there's a really long way, Cineo, of saying yes to your question. Yuntron is saying, so the pitch is just a brief on the technique points on assignment 3 is the correct way of thinking. Yeah, think of it like this, though. Think of it as like, we want to build this kind of virtual world. So we want to build a combat arena for cars to play soccer. And we're going to call this Missile Arena. So it's cars playing soccer in this arena. So what we're going to want for this is a particular kind of tech. This thing is going to be viewed kind of from just behind a vehicle. So it's a slightly larger scale. But that's not going to change our renderer too much. But we want this to be flashy and sporty. So we want a lot of lighting. Maybe we want a deferred renderer for this lighting so we can have a lot of headlights and all these like little lights everywhere, and we're not going to bog down our scene because of that. We're going to have a massive amount of specularity in things because it's like a big metal arena, right? And so what we're going to do is we're going to make sure that we have the capability for, say, planar reflections in some of these. We can't do it for all of them, but maybe some of them. And also really, really in-depth let's do some physically based rendering for the different materials that the cars are made of and stuff like that. But that's kind of where we're at. We don't think we're going to need very high quality animation in terms of like all of our objects are solid, so we don't think we're going to need like skeletal skinned animation systems or anything like that. We might be wanting to throw in some massive particle systems, so we've got like all these extra visuals happening when stuff happens. We're going to need some use of transparency because some of these vehicles are going to have windshields and just transparent parts, I guess. But I think that's where we're at, right? So there's my design pitch for Missile Arena. It's like a rocket arena. So yeah, I'm just saying this is the tech that we need to do this. So this is like an engineering design pitch in a sense, where we're saying, like, not only did I say, hey, here's a cool idea of this thing, but here's how we plan that it should be implemented. Here is the bits of technology we think is needed to make this work. Yunshun's saying, does it have to be a game or a story? I would say that, yeah. I would say you could say this is a short film, a CG film, and it's going to need these bits and pieces. So you could talk about this as if it's not real-time rendered. I mean, you're still going to have to do real-time rendering stuff in the assignment because that's the only tech that we've taught you. But you could say that this is a short film that goes through these settings, and these settings are going to require these techniques to look right and stuff. It doesn't have to be a story or a film. You could also say this is a virtual reality educational system for deep sea diving. In order for this thing to achieve its goals, we need to be able to show certain things at a certain level of realism, and other things are not necessary because it's an educational simulation. It's not needed to entertain, you know. So then you'd have a different set of requirements and things like that. So think up an imaginary system and think up what might be needed to be able to implement that system. Hexus One's asking, can we 100% the assignment with a 2D game? So I'm mentally going through the criteria. No, you can't. The things that you will not be able to do in a 2D environment, you will not be able to show that you're doing shadow mapping. You could do an entire deferred rendering shader for 2D, and you'd be wasting a whole lot of processing and video memory, but you could still do it. But shadow mapping will just basically not exist in a 2D environment. If you're going to do a 2D game, can I suggest you can do all of the requirements of the assignment if you do something like a 1980s beat 'em up, like a Streets of Rage or a Ninja Turtles arcade game or X-Men arcade game kind of thing. You could do something cool like that. Someone's saying Octopath Traveler. I think that's the kind of thing where you've got flat things, but they have depth. So you can do that kind of thing. Sinio said this is going to be like UML for 2521 where we code first and design accordingly. You can if you want. I mean, like, you know, like the subjective marks that we've been talking about giving everyone in each assignment, that can be definitely written after you've finished doing things. Because you go, well, I did all these things and I thought they're really cool. And then I had to rejig them all to put together into some way that looks cool. And then I wrote about it. I wrote my story after I'd finished my tech for it. I mean, that's what Far Cry and Crysis were. Those games were built for the engine. They were like, what does the engine do really well? Now let's make a game in those engines. You know, the reason why they were on tropical islands for so much of the early days of everything that's in CryEngine was just to show off the CryEngine was like, we can do long view distance with foliage. It's like, well, fine. We'll just make everything long view distance foliage. And it's like, have you considered gameplay? It's like, no, long view distance foliage. Gameplay comes second. Crysis was famous for that. Having said that, still a very good game. So they got lucky, I think, in terms of like being very good graphics programmers that happened to be able to design a game. I think id Software, the early Quake, had one very good graphics designer and then like two very good gameplay designers. So they got a balance there. In this course, I don't care about your gameplay. There is no gameplay. There can be no gameplay. Like, I'm not asking people to do things like player controllers, follow cameras, collision detection, physics, NPC, AI. There's so much stuff in games that we haven't covered at all. We're just purely looking at your rendering tech. in this assignment. So even though I'm trying to get you closer to the idea that rendering tech is built for a purpose, it's built for a game, it's built for a movie, it's built for a reason. I'm not expecting you to actually implement the full reason for it. So if someone starts putting like, first person shooter guns in games that can actually hit targets and stuff like that, yeah, you'll get some subjective marks for that, but that's so much work for just the subjective marks. Not that I haven't seen a lot of people put in a rather disproportionate amount of work for subjective marks, but that's up to you. Okay, so what are people saying? So Kumash is saying the design pitch also contains any specifications of what we didn't get to implementing. Yeah, you can even, as I did in my design pitch, you can say, I have no intention of implementing this, but I think it's going to be needed. So you can be like, this thing's like, it's a house of mirrors. Normal planar reflections with this many mirrors is not going to work. You need ray tracing for this. I have zero intention of implementing ray tracing in this assignment. You can say that, that's totally fine. So the design spec is basically, it's nearly decoupled from the rest of the assignment. It's better if it's coupled, but it's decoupled in a way that it doesn't force you to implement anything, the design spec. It forces you to think about what might be needed. So in every engineering process, there's always someone that looks at the requirements. So it says, okay, the game designers have pitched us this world, and the artists have drawn all this concept art. This is the tech we need to do that. And then we pass that down the line and someone else says, we don't have time for that tech. Which of these bits are we going to drop? And he's like, okay, that's fine. We'll drop this, this, and this, and we'll do these things and we'll get enough. So the design pitch is before we've decided what's feasible. So you can say it needs this, it needs this, it needs this. You don't have to say we have done this, we've done this, we've done this. Because it's prior to what we've done. Supersonic acrobatic rocket powered battle cars. Yeah, totally. That was the Rocket League thing that I was doing. Wait, did I call it Rocket League? No, I called it Missile Arena. What was I calling it? Yeah, anyway. Oh, David, if you're having trouble accessing your Git repo, it's because it doesn't exist yet. Sorry, I forgot to put that in my announcement. I was written down as a list of things that I was going to put in my announcement, but I forgot to say that the repo will be coming in the next couple of days. Oh, wait, did I say that in the announcement? I can't remember. I don't know, but your repo's coming in a couple of days. I haven't even written the stub for the justification yet, so you can see the spec. But I apologize, can't jump in just yet. Software is catching up. We'll be there in a second. Yundron's asking if I am a thesis supervisor for honors years. I'm not at the moment. There's a chance that I would take on some thesis students in the future, but I have not yet. I've been focusing all my time and effort on education delivery instead. I've supervised one research student for a Taste of Research scholarship. Apparently that was lit, so I'm happy with that. But I haven't done any more than that. So I think a thesis would be a step up from that and would take a lot more time from me, which is time that doesn't go into stuff like this, if that happens. Senior's like, you wish assignment 2 also had a design pitch because you bombed it, but you wrote some original vision. Well, if you have that original vision, you could copy paste that into assignment 3 and then see if you can implement it in assignment 3. Because if you haven't submitted it previously, then you can use it. I don't know. Your vision for assignment 3 might be different from what it was for assignment 2. But at least you've practiced. You know how to write the pitch. It's more important that you learn it than you get marks for it, David's asking, can we build off assignment 2 and add all the extra features required to assignment 3 and submit that? Yes. Your work, you've done it in the course. I'm not considering your own work in the course to be possible to be self-plagiarized, in a sense. Like, if you want to in this course, like it's a bit late now, but you could have had the same project in all 3 assignments, where the first project is like your assignment 1, second project just takes your assignment 1 and extends it into 3D. Third project adds all this post-processing and all this like extra kind of nifty little features on top of the same setting. So if you want to, like if you did something like model importing or something like that, you go, I'm just going to use the same model, but this time it's like Chrome. So we take Metal Mario, right? We take Mario, it's the same model, Mario, and we go Metal Mario. We put it in an environment map, right? And that's an easy extra in a sense that you can do. So you don't need to go and find new models. If you want to continue on the same theme, you totally can. One more reason to procrastinate and do other things. Oh, right, like you're talking about the software side of the assignment not being ready yet. Oh, right, David said that's true. Okay, it was in the stuff I said I was going to say, and I did say it. That's good. So the notice did say that the software's coming out tomorrow, maybe even tonight. We may have it finished tonight and get it out. But I mean, it's like 6:30. I did need to actually stop working at some point. I've been working all weekend, so at some point, and I haven't written the Wednesday lecture yet. So there's stuff to do. I will do it when I can. But I do want the repo to be ready before the next lecture. But I say I do want to. That doesn't mean I can magically create extra time for me to write the justification stub to go in there. Ningoan's asking, if I did not finish multiple lights, what will happen to my assignment? 2 marks. Should I submit it later or not, since the penalty is 60%? I don't know. You have to decide that yourself. So if you are above 40% of your total mark at the moment, and you can kind of tell that by looking at the spec and your justification, so the bits where you know you've put in your justification, if that is above the current like ceiling that your late penalty is, then let it go, you know, because if you're going to reduce your marks by submitting it again, then that's a bad thing. But if you think that the amount of work you've done is not up to the current ceiling, which is 40% of the total marks, and you can get closer to 40% by adding something and submitting it now, then go ahead and submit. But this decision is yours. We're not going to mark your assignment twice and give you the highest mark out of the 2 possibilities. That's just something that's... Otherwise, then we'd open ourselves up to marking like 8 different versions of every assignment and seeing the curve of the late penalty and doing it. The late penalty is just there to make sure this thing gets finished, you know? I would say potentially you've already finished it and you're already above 40%. If you've done everything, but the only thing you're missing is like multiple lights, like I have a feeling you've probably got enough marks as it is, but I don't know, right? You have to decide this based on how many marks you think you have. Because you could have done other parts of the assignment and you're well over 40% in the assignment and you're fine, you know? These questions we must answer ourselves. Okay, I'm going to wrap it up there. I think I've answered all of the questions that were in chat that we're talking about, and hopefully I've given you some examples of some of the things that you might want to think about for the final assignment. Good luck to everyone, but this isn't goodbye yet. I will see you on Wednesday. Wednesday will be goodbye, though. I will see you all on Wednesday. Wednesday, we're going to talk about a few different things. I'm going to talk a little bit about optimization, and I'm going to do a grab bag of techniques that I'm not going to show you. Techniques that are cool, techniques that are interesting. Some of them are deeply entrenched in the kind of graphics that we do. Other things are just kind of additions, in a sense. Things that might flow on from ideas. Things that are undoubtedly visual graphics, but they're not part of the sort of polygon rendering pipeline, in a sense, but they're still, like, you know, important. I'm gonna see if I can do just like 10 minutes on each of those just to say what they are, and think about the future. And that's my vague plan. Okay, thank you all, and I'll see you on Wednesday.